Let us see a more interesting example of the same formula. In this case, you have n sticks of different length. We can actually sort these sticks by their length. So we keep it like this, and then we say that this is the first stick, this is the second stick. There are n sticks like that. So first stick is the smallest, nth stick is the largest. That's how we have numbered them. And we have n holes where we are going to place the sticks randomly. Sticks are placed in n holes randomly. Now we are viewing from the left. This is an eye. So if we see it from here, question is, what is the probability that the stick at the kth hole is visible? Now you realize that if there is any stick which is bigger than the kth stick before it, then we will not be able to see it. Remember that we are viewing from here. And then if there is a bigger stick, then it will block our viewpoint. So if we pick the sticks randomly, what is the probability that the kth stick is visible? We kind of have to use the partition formula. That's how I have started this lecture. So that's not surprising. But question is, how should we partition? And one of the natural partition is that AI is the event that the ith stick. Remember, we have sorted our sticks by their length. So ith stick means whose length is at the ith number. So ith stick by length goes in the kth hole. At least one of the stick has to go to the kth hole. Assume that the ith stick has gone. This is the case AI, and B is the case that the stick at the kth hole is visible. Now we are interested in calculating the probability of B. We know by our formula it is this expression. So what are these individual values? Now it's easy to see that probability of AI is 1 by n for all I, because it's equiprobable which stick I will choose for the kth stick. What about probability of B given AI? This will require a bit of thinking. If the ith stick goes at the kth hole, that means the first k minus 1 sticks should be small. That means these k minus 1 sticks should come from the I minus 1 sticks, which are smaller than the ith stick. In this case, it can choose as I minus 1 choose k minus 1, and then they can be arranged in k minus 1 factorial. The ith stick goes at the kth hole, and now I have n minus k sticks remaining, which can be again permuted arbitrarily. So these are the favorable cases, and if the ith stick is going at the kth hole, that stick is fixed, remaining n minus 1 can go as possible. So this is the probability of B given AI. This is the total cases. As an exercise now, calculate probability of B. So this is just some calculation. You have to be smart about it, but you can figure it out. What I'm more interested in is a different division. We will see that by tweaking the cases, we can actually get the answer very, very easily. So again, we are going to calculate the probability of B, which is that the stick at the kth hole is visible. The partition is going to be different. What is the partition? I will index it by a subset S. S is a subset of n sticks and size of S is k. So this denotes that the sticks from S go in the first k holes. So instead of saying what sticks are going at the kth hole, I fix all the sticks which go at the first k holes, and then they can arbitrarily put. If this is the case, again we are interested in finding out probability of AS and probability of B given AS. This should tell us probability of B. Now this is a question I will not worry about it. You can calculate if you want to. What about this probability? If I have k sticks fixed from a set, I can only see stick at the kth hole if it is the biggest stick in the set. And the biggest stick comes at the kth hole with equal probability. This is the important observation to make it work. This will only happen with probability 1 by k. Since every stick from S is equally likely to come at the kth hole, the probability that the biggest stick comes at the kth hole is 1 by k. And this is the only case when the stick will be visible. We know the important quantity. Let's apply the formula. Probability of B is summation over S, probability of AS, probability of B given AS. I can take 1 by k out and this becomes summation over S probability S. Now this thing trivially should be 1. Why? Because our all cases are all encompassing. Since every case is covered by this ASS, then the probability should be of the entire sample space, which is 1. So we get directly the probability 1 by k, which we got by some difficult calculation in the last case. Armed with the knowledge of conditional probability, we will go into another concept of independence. I'm going to briefly introduce it, but this is going to be very, very important in the course later. We will actually devote close to a week on this concept. So at least get started. What is independence? Again, we will start with an example. Suppose you throw a dice twice, and the question is, what is the probability that you observe same number on both the throws? You can easily calculate it. I will call it event A. But now, suppose I am given event B, which says that the number on the first dice is prime. Does this affect the probability that we get the same number? Let's define another event C, which says that the sum of the numbers displayed in these two throws is prime. And let's say event D, which says that the sum is less than equal to 5. What do you think? Should the probability of observing the same number change? The easiest case to answer is C. You would see that if the sum of the number displayed is prime, then probability of A should become 0. Also in B, you might think that it should not matter whether the first number is prime or not. Whatever be the first number, the second number being the same as the first number happens with probability 1 over 6. This should not affect the probability of A, and you would guess that it stays 1 by 6. And actually you can prove, you can look at the cases and you can see that it is going to be 1 by 6. D is more complicated and you have to calculate this quantity. What is the message here? The message is looking at events such that probability of A does not get affected by event B. These are the interesting cases. Like in the previous case, whether the first number we saw was prime or not had no bearing on the fact that both numbers were same or not. So in this case, we say that A and B are independent events. How do we define it mathematically? The intuition again was that probability of A given B and probability of A should be same. Knowing B should not change the probability of A. We can define A and B being independent as probability of A being equal to P of A. This means A and B are independent. though we change it slightly. Instead of defining like this, we say that probability of A intersection B should be equal to P of A multiplied. Then we say that A and B are independent. You might be curious that why should we define it in a different way? First thing to notice that this is exactly equivalent to this definition if probability of B is non-zero. So this is one reason why we defined this way, so that we don't have to worry about the case when probability of B is 0. If that is the case, probability of B is 0, then this quantity becomes non-negligible. Another thing is that this definition is symmetric. It directly tells us that if A and B are independent, then B and A are also independent. This definition we have to stare for a while, but this directly implies the symmetric property. That's why we prefer this thing to be the definition of independent. So just to get these concepts clear, we will take an example and see if we can figure out whether the two events are independent or not. Let's say we have a box where we have four balls. Two of them are blue, two of them are red. We pick two balls, one after another, and define two events. R1 is the case that the first pick is a red ball. Similarly, B2 is the event that second pick is a blue ball. So the names kind of clarify what the events are. And then the question is R1 and B2 event independent? Say R1 and B2 independent. If you think about it for a while, the question is not well defined. We say that the distribution is picked with replacement if after picking the first ball, we replace the ball. So in this case, whether the ball comes out as red or blue, then we keep the ball back. If this is the case, it is quite clear that probability of B2 given R1 is still half. Because even after I pick the first red ball, I will give it back. Again, the urn will look completely the same. I have two blue balls and two red balls. So probability of B2 given R1 is half, and we also know that probability of B2 is half. So these two events are definitely if the selection is done using replacement. Another thing is without replacement. That means we pick the first ball and then throw it away. Intuitively, the probability should change. So let's calculate what is the probability of B2 given R1. Once I have picked the red ball, I will throw it away. So then the urn now contains one red ball and two blue balls. So then this probability becomes 2 by 3. On the other hand, probability of B2 remains. If it was without replacement, then they are. So this was a brief introduction to what independence is. We will go into detail later. Next lecture, we will learn about something called Bayes' theorem, which allows us to calculate conditional probability easily. This is going to be the target for the